we need to address everyone's favorite topic now, stereochemistry. And we need to dovetail that stereochemistry in with our elimination reactions. This is really important because we're going to see how that stereochemistry flows through. Is there any stereochemistry with alkenes? Yeah, we know that alkenes have stereochemistry. They can be either E or Z, right? Or cis or trans, however you want to look at it. But that stereochemistry that alkene is going to have is going to flow from the stereochemistry, of course, of our elimination reaction, if that is what's going to occur. So to talk about that, we need to talk about how elimination reactions work and how they're so effective. An elimination reaction is really, really effective, as you remember, again, because if we look at our two carbons, we have a proton here, and we have some leaving group here. That leaving group is really electronegative, so it's pulling its electrons really hard. And this proton, of course, is not holding on to its electrons very hard. It's just a hydrogen. So if it's grabbed by a base, because of its strong dipole, these electrons are flowing in this direction. Now, the reason this is so important to remember is because there are some orbitals going on here. If you recall, there is an orbital that this is leaving, and there is an orbital that these electrons are in. And what those electrons end up forming are 2p orbitals. And when 2p orbitals link up with a pair of electrons, we call that a pi bond. Now, this is really important to think about because the geometry of that pi bond is what ends up leading to the stereochemistry of our original reactant and product. If you look right here at this stereochemistry, these have to be lined up. Well, let's go ahead and look at our reaction and see if we can see how that works. Well, if you think about an E2 reaction or one of these really common elimination reactions, what we're going to have are two carbons, and I'm going to represent those two carbons with a Newman projection so we can see the result and how this works. And let's say we have some hydrogen here, and then we have a CH3 and another CH3 over here. And now let's say in the back, we have our leaving group, whatever that leaving group might be. And then we also have a CH3, but here we have an iso group. So could this reaction happen right now? Could we just come along with our base and go ahead and grab that proton? Well, it turns out we can't, because if you look at the orbital that proton exists in and the orbital our leaving group exists in, they're in different places. They don't line up, so that's not going to work. What we're going to have to do before we can do that is allow this entire molecule to rotate.
As we rotate around the carbon-carbon bond, trace where each atom ends up. When the hydrogen and the leaving group are opposite one another like this, we call it anti.
But they're in the same line. So this means that if we took our base and we grabbed this proton, these electrons right here would be able to flow into this space between these two. Specifically, you notice that these electrons will be building density here. Now, if you remember, that leaving group has a bond, but that leaving group also has an anti-bonding orbital that has density here and here. Now, if you look and pay close attention, those electrons from that hydrogen that are flowing along the back side there are going to be flowing into those anti-bonding orbital there, and allowing us to push this off. That is how we're going to break this bond and remove our leaving group. So you see here that these always have to be anti. Now, this is an interesting point because let's look at two examples of some anti things. Pretend we have one example that has a leaving group here in the front and then pretend we have, and I'll just draw it anti to help us out. So we have a proton here and a leaving group here. Now I'm going to use two examples of this. So let's say that in one example, we have a CH3 here and a C, we'll do an iso group here. And then over here, we have an H and an H. Versus in this example on over here, we also have the iso group here, but our CH3 group is over here in this case, and our H's are going to be in these positions. So what would the result of these two reactions be? Well, if you notice, we're of course going to take these two hydrogens off, which is sort of going to flatten these out. Notice if we take the hydrogens off and the leaving group, what's going to be left here? We're going to move these up and these down to make a flat plane, because those p orbitals here on the front and the back are going to form that pi bond. So what do you notice this is cis or is it trans? Well, look, we have one on either side of this double bond. This is actually looking from the top, going to look something more like this.
Draw the methyl group on the rear carbon and the iso group on the front carbon.
So we notice this is trans. However, if we look at what would come out of this group over here,
both hydrogens go on the left side and the iso and methyl on the right side.
So this is going to be cis, right? So that is where we get our stereochemistry from in our elimination reactions. Now I want to add one more important flavor to this, and it's a really actually kind of a complicated one, so bear with me. What if we have a ring that we're eliminating from? So what if we have something more like this? Well, it's interesting because really this is drawn flat, but we all know that really a ring is going to form a chair. What's important about the chair is that we have different groups here in different positions, right?
We can draw both axial and equatorial groups at one carbon and at the other carbon.
It turns out that these two groups are actually, if they're axial, they're actually going to be anti to one another. Let me bring in a graphic from our lecture to show you what I mean. So if you look here, now that I've brought this in, you notice in their better drawing than mine that the base can grab this proton because its electrons will flow into this p orbital, breaking this bond because that's an anti-bonding orbital, and that can leave. That can only happen in the axial position. If they're equatorial, these groups will not be able to eliminate. If in this position we have a bulky group here, notice I've circled the equatorial. If you have a bulky group there, this reaction will speed up. Whereas if you instead had a bulky group here, the reaction would slow down. Why? Well, because that bulky group wants to be equatorial. So the ring would flip, moving both of the things that are actually reacting into the equatorial position where they could no longer react. So that is how these reactions are controlled by the fact that they need to be anti. And we call this literally anti-coplanar because they are in the same plane, though they are anti to one another. So always look for that and how that stereochemistry controls these reactions.